Hello everybody, welcome back to the third instalment, but chapter 1.5 of data collection. So it's the first chapter of the year 12 statistics bit of the course. So we've seen lots and lots of definitions so far, different sampling techniques, but now what we're going to have a look at is something which runs throughout the stats mechanics portion of the exams, could be asked here and there at any point for a couple of marks here, maybe 1 mark there. Is something called the large data set. So I'm going to introduce you to it here, give you a run through of the key concepts and takeaway points you need to remember, and then also some general advice in terms of how to keep your mind fresh so that when it comes to the big day you can remember all of these pointers. So anyway, let's get warmed up with this activity. So there's some words to fill in to these sentences here, so it's just a case of going over the last couple of lessons worth of definitions and knowledge and just getting your head into definitions of what those things were. So pause the video here and try this, and when you're ready to see what the solutions are, press play and we'll go through it. Okay, so let's have a look at where these words go. So, first of all, data that is collected directly for yourself is called primary data, whereas data taken from an existing source, such as a book or a website, is called secondary data. So I'm just crossing these off as we go. The most common methods for collecting data yourself are to perform an experiment or to complete a survey. If a sample of data is collected, ideally it should represent the whole picture, which is called the population. This means the sample needs to be of an appropriate size and must avoid bias. Questions should not be leading, but could allow only specified answers, which is what's called a closed question, or any answer, which is called an open question. Surveying every member of the population is called a census, and sampling by taking a lottery or drawing names out of a hat is called taking a random sample. Sampling every 5th, 10th, 15th and so on item or similar at regular intervals is called taking a systematic sample, and taking a sample from each subsection of a population so each group is represented in proportion to the population is called a stratified sample. As well as the type of data being collected, other factors influencing which method to use include both cost and time. If you put time and cost the different way around, that's absolutely fine. Cost, time cost, whichever. Data can either be numerical, numbers, or it could be non-numerical, in other words, described as words. Data that can only take specific values is called discrete data, whereas data that can take virtually any value in a given range is called continuous data. Once data has been collected, it can be put into classes to make it easier to analyse, and this is called grouped data. So well done if you got those words in the correct places, and well done if you did it fairly quickly without using your notes too much, but the main thing is that's where the words go. So let's move on to what's this new thing called the large data set. So the large data set, let's get straight to it. So you'll need to answer questions based on real data in your exam. So some of these questions will be based on weather data from the large data set, which is provided by Edexcel. So this is a QR code where you can scan from your worksheet an online version of the large data set, which I've put up. Now, of course, if you're watching this already online, you can just do a quick Google search, large data set Edexcel. It's readily there. So there's lots of data when you do actually load it up and look at it, but don't worry, you're not expected to memorize all the data. If you've not looked at it yet, it's a fairly big spreadsheet with multiple tabs on it with lots of different figures and facts. So if you don't need to memorize all of it, then what bits do you really need to know? Well, the data consists of weather data samples provided by the Met Office for 5 UK weather stations and 3 overseas weather stations over 2 set periods of time. The first set period is from May to October 1987, and the other set period is from May to October 2015. So it's only for 2 different years, and for each of those 2 years, it's only half a year each time. From May to October is only 6 months out of a full 12-month calendar year. The weather stations included in the larger data set are shown in these 2 maps following. So the first one, these UK weather stations. So we've got Camborne down south, Herne, Heathrow, Leeming, and one in Scotland, which is pronounced Lucas. And there's also some overseas ones, which are here. We've got Jacksonville in the USA, in the Northern Hemisphere, Beijing in China, and Perth in Australia in the Southern Hemisphere. So there's only 3 overseas ones. The large data set contains data for a number of different variables at each one of these weather stations. So the first thing is daily mean temperature. This is recorded for all the weather stations. It's measured in degrees Celsius, and this is the average of the hourly temperature readings during a 24-hour period. The next thing is daily total rainfall. This is going to include solid precipitation such as snow and hail, which is melted before being included in any measurements, of course. Measurements less than 0.05 of a millimetre of precipitation are so small, they're just recorded as TR, or trace. So TR, or trace, stands for the same thing. It just means an amount of rainfall which is so negligible, it's barely worth even mentioning at all. And another one is daily total sunshine. This, you probably could have guessed, this is measured to the nearest, not hour, but nearest tenth of an hour. You probably would have guessed it was nearest hour. I fooled you, if so. No, it's the nearest tenth of an hour, so in 6-minute intervals. A big one to consider is daily mean wind speed and direction. So, wind speed is measured in knots, averaged over 24 hours from midnight to midnight. Mean wind directions are given as bearings and as cardinal, which means compass directions. Wind directions say where the wind is blowing from. This is a really important point. It's where the wind is blowing from, not the direction it is blowing to. So, for example, if this was an arrow explaining the direction of the wind, this would be a westerly wind. It's pointing east, but it's originating from this end, which is the westerly end. So because it's going from west to east, it's westerly, not easterly. These are the cardinal wind directions as well in this little diagram. So they can be given as one of 16 directions actually. You will have known of north, east, south, west, and almost definitely will have known of northeast, southeast, southwest and northwest. And you may well have known, but not necessarily known, that between north and east there are also extra ones as well, beginning with north, northeast, which is 22.5 degrees bearing away from north. So there's 16 directions in total. North, NNE is north-northeast, NE is northeast, and so on. You can read them yourself, so from me just reading them all for you. If the wind direction were assumed to be random, you could say that the probability of a wind direction being east-northeast, for example, would be 1/16. The data for the mean wind speed is also classified by the Beaufort scale as well, which has a list of different numerical values relating to things that can be observed at the time. So, a Beaufort scale of 0 means absolutely calm. The wind speed is less than 1 knot, can barely feel any wind. From 1 to 3 is a light wind or light breeze. Moderate means you can definitely feel a wind is blowing. And 5, 17 to 21 knots, that's a fresh wind, that's quite windy. Not that I'm very scientific when it comes to describing the weather, as you can no doubt tell. By the way, 1 knot is 1.15 miles per hour. So very, very roughly speaking, 1 knot is about 1 mile per hour. Next up, we've got daily maximum gust. This is measured in knots as well, and this is the highest maximum wind speed recorded. The direction from which the maximum gust was blowing is also recorded too. Then we've got to consider daily maximum relative humidity. This is given as a percentage of air saturation with water vapour. Relative humidities above 95% give rise to misty and foggy conditions. And also there's daily mean cloud cover, and this is a weird one, it's measured in octas, or eighths of the sky covered by cloud. So octas, thinking of octagon or octopus, whatever, octas means eighths. So 0 would be a virtually clear sky, 0/8, and 8/8 means virtually total cloud cover. For example, on an autumnal British day in October, I don't know. So a common mistake here is because it's measured in octaves. People would guess the probability of it being, for example, 5 octaves would be 1/8 because it's divided into eighths, but never discount the possibility of it being 0/8. So it could be 9 possibilities, 0 octaves all the way up to 8 out of 8 octaves. Finally, we've got daily mean visibility. and this is measured in decameters, which is tens of meters. It's the greatest horizontal distance at which an object can be seen in daylight. Oh, one more, sorry. Daily mean pressure, almost forgot. The daily mean pressure measured in hectopascals, and that's the same as a millibar. The average pressure at sea level is 1013 hectopascals. Something like 995 hectopascals would, on the other hand, be considered low pressure, and 1025 hectopascals would indicate high pressure. So don't be thinking 1000 is average, just be thinking that probably average-ish is about 1008, 1010, somewhere in that region. Any missing values in the table are indicated as NA, or not available. And by the way, for overseas locations, only daily mean temperature, daily total rainfall, daily mean pressure, and daily mean wind speed are recorded. So for the overseas ones, there's not as much information there for them. It's useful to bear in mind some general trends with a larger dataset, and some of this boils down to common sense too. So generally speaking, wind speeds tend to be higher for stations near the coast, because we're nearer to the sea, and the sea generates wind because of the waves. So for the UK ones, that's Herne, Camborne and Lucas in Scotland, and in the US, Jacksonville is also coastal. Daily mean temperatures tend to be higher for stations near the equator, again as you'd guessed, particularly Beijing and Jacksonville. Daily mean cloud cover is negatively correlated with daily total sunshine, again a bit of common sense there. The more cloud cover you have, the less likely it is you'll have much total sunshine that day. High pressure tends to suggest more settled weather conditions and better weather generally. Low pressure usually suggests unsettled conditions and rain. So high pressure, good. Low pressure, bad. If you like the sun, that is, and nice calm weather. Daily mean temperature tends to correlate positively with daily total sunshine. Again, a fairly common sense general correlation. Again, one of these correlations to bear in mind, daily total sunshine tends to correlate positively with daily mean visibility. There are, of course, other conclusions to draw, but remembering the above is a solid start. Even though you don't have to commit the entire dataset to memory, it still is a lot to digest. Take in what you can, but as an absolute must, do remember to refresh your memory of the larger dataset shortly before your exams. You're doing it almost the first thing in year 12, and then you have to remember it at the back end of year 13, so there's almost a 2-year gap in between learning it the first time, then returning to it. So if you don't refresh your memory from the first time, which would be silly at the best of times, then you're going to be really struggling. So as an absolute minimum, this needs to be refreshed shortly before your exams. If you do need to do any calculations on the large dataset in your exam, the relevant extract from the dataset will be provided for you. You need to be familiar with the types and ranges of data in the large dataset and with the characteristics of each location as well. You may need to recall trends from within the dataset or identify location based on some given data. Moving on, let's have a look at a worked example. I apologise for this table being on its side. I didn't know how to squeeze it down in terms of size yet still be legible, so you sort of tilt your heads, or you can sort of imagine reading it upside, well not upside down, but from top to bottom. So again, not the best editing, but there you go. Anyway, this is an extract from the large data set itself. It's from Herne. It says first of all to describe the type of data represented by total daily rainfall. Well, rainfall is of course, it's going to be quantitative because it's given as a number, and rainfall is a volume, it's a capacity, so it's going to be continuous as well. So the best full answer to give for A is that it is a continuous quantitative data. Next it says about Alison, who's investigating daily maximum gust. She wants to select a sample of size 5 from the first 20 days in Herne in June 1987. These are the first 20 days from the 1st here to the 20th down here, which would have been at the bottom if the table were the right way up. Apologies. So she uses the first 2 digits of the date as a sampling frame and then generates 5 random numbers between 1 and 20. This is a bit of a definition memory test really, nothing more. Just state the type of sample selected by Alison. She has done a simple random sample. Part C, it says explain why Alison's process might not generate a sample size of 5. While some of the data isn't available because it's listed as NA. So for example, if she's trying to find the first 20 dates in Herne and she wants to look at the gust, you can see here the maximum daily gust. That's not available, and this one's not available as well. So she'd have to account for those. If she didn't, then it wouldn't necessarily give her a usable sample size of 5. Let's use the same excerpt, the same section of the large data set for a second worked example now. So worked example 2, let's calculate the mean daily temperature for the first 5 days of June in Herne in 1987. So the first 5 days are the 1st, 2nd, 3rd, 4th and the 5th. So they're going to be these ones here. So these are the first 5 daily mean temperatures for the first 5 days in Herne, in 1987 anyway. So to find the mean, obviously we add all the values together, so 13.1 plus 15.5 plus 13.8 plus 12.5 plus 15.1, and because there's 5 values, we divide that by 5, and that would give us 14.0 Celsius if you round it off to 3 significant figures or 1 decimal place. Part B, it says the median daily total rainfall for the week of 14th of June to the 20th of June inclusive. So that's the next thing we need to find. So from the 14th of June to the 20th of June are these last 7 days. So we're looking from the 14th to the 20th. We want the daily total rainfall, so we're looking at this row here. So therefore we're looking at these values. So if you put these values down, just write them down, we're going to have 0, TR, which I've ringed in red. TR just means trace. 7.4, 0.1, 5.6, 3.7 and 0. This is a really good example to show you because it teaches what to do and how to account for TR values. Well, TR just means anything less than 0.05 of a millimetre of rain. It's basically so tiny it's negligible. So the TR entries could be replaced with zeros if you need to perform numerical calculations on the data. And doing that is called an example of cleaning the data. This is one way of just making the data computable. So you're taking something which a calculator can't compute, TR, and replacing it with a very, very good approximation to what TR is, 0, and a calculator can deal with 0. So if I just replace the TR with a 0, the data then becomes this, with TR replaced with 0. I'll put this 0 in red so you can see that you've got the 0 which was your original 0, plus now an extra 0 from the replaced TR entry. And now just remember, because we're trying to find the median, we need to put these values in order of size. So from smallest to biggest, in numerical order, we've got this. So the median isn't going to be the first or last, so you can cross those end ones off. Not that 0 or 5.6, not that 0 or 3.7. The only one left on the middle is 0.1, so our median must be 0.1 millimetres. Worked example 3 is one I've just taken and adapted from an actual past paper. It says here that Jerry drew this scatter graph below using the June 1987 data for Camborne from the large data set, but oh dear damn, he forgot to label the x-axis. Using your knowledge of the large data set, suggest which variable the x-axis could represent. So this needs to get you thinking. So a thought bubble. What quantitative values correlate positively with daily mean visibility? So when a day is clearer, what also tends to be true? Well, temperature tends to be higher. If a day is clearer, normally it's when the sun is shining better and brighter, the temperature tends to be, as a general rule, a bit higher. Well, it can't be temperature. Why not? Let's just have a look at this scale. So temperature is going to be measured in degrees Celsius. And this is for June 1987. Would you have lots of 0 degree Celsius days in June, which is midsummer? Basically days where it's literally freezing in June. And lots of ones where it's literally colder than a fridge. So no, it's not temperature, but it's not wrong to be thinking that in the first instance. Another thing you might be thinking is pressure. The higher the air pressure is, the better the weather, generally speaking, and the better therefore the visibility would be. But again, it can't be mean pressure. Why not? Again, it's because of this scale here. Pressure is measured in hectopascals and tends to be something like 900s or thousands. So these are far, far too low to be the right figures if it were to be mean pressure, which would be being measured. Hours of total sunshine is actually the only one left which does correlate positively, which is what it could be, and in fact it is hours of sunshine. So for example, if a day's really, really cloudy from minute 1, it's just really rainy and really cloudy, you might have no hours of breakthrough sunshine. Whereas on a good clear day, it could be a good 10, 11 hours worth of sunshine if the sun is out and it's not too cloudy in the sky. So the actual one you'd have to go for there, through like a process of elimination, to show that it can't be temperature or mean pressure, would be hours of sunshine. So that one is just to say hours of sunshine. So that's just a quick example showing that some knowledge and common sense of general trends of weather can be used to help you score some marks in the assessment. In a similar way, let's have a look at another one from a past paper, which again relies on correlations and trends. So this one here, a random sample of 15 days is taken from the large data set for Perth in June and July 1987. The scatter graph here displays the values of 2 of the variables for these 15 days. Describe the correlation. You're not dreaming, that was actually a question. It's only 1 mark, but yes, it is as simple as just saying negative. Straight line, line of best fit would go through here, and it would be negatively correlated. It would be going downhill. Moving on to part B, the variable on the x-axis is daily mean temperature, measured in degrees Celsius. So now we know that this is temperature on the bottom. It says now to use the knowledge of the large data set to suggest which variable is on the y-axis. So it's not saying which one is it definitely, but what variable could it be? So again, let's just be thinking. What correlates negatively with temperature? Because again, this is negative correlation. Could it be pressure? Well, actually, pressure tends to correlate positively with temperature, so it's probably not pressure. So we'll explain why it might not be pressure in a moment. Could it be cloud cover? Well, it couldn't actually be cloud cover either, but that's not quite so obvious. You'd be thinking, well, cloud cover is surely negatively correlated with temperature, right? I mean, the higher the temperature is, then the cloud cover must be lower because more sun's getting through. And the higher the cloud cover goes, then the lower the temperature goes, because the higher the cloud cover, the less sun's getting through. So you'd be thinking that were true. However, the key thing here is in these scales. Okay, look at the increments on the y-axis. Cloud cover is measured in octas, and so the scale wouldn't be eighths, remember, there'd be 9 different octas. 0 octas, 1 octas, 2, 3, 4, 5, 6, all the way up to 8 octas. So these would have to be going up in eighths, and they clearly aren't. The scale's clearly going up in something much, much tinier than eighths, or there's at least, we can say, more than 8 possible values that y could be taking. For example, I don't know, if that were, say, 1/8 maybe, is that going to be 2/8? Does that look right? And if that's 2/8, is that 3/8? And is that 4/8? The scale just is totally wrong for it to be cloud cover. So not as immediately obvious, but thinking through the scale, it can't be cloud cover. Could it be then rainfall? Is rainfall negatively correlated with temperature? Well, generally speaking, yes. The higher the rainfall, the lower the temperature. Rainy days tend to be colder days. So that is a correlation which does hold true. So it could actually be rainfall. So I've included cloud cover as a possibility because you might be tempted to think cloud cover would fit for correlation. I'm just explaining why that isn't a valid answer because of the scale. However, weirdly, pressure, although it's unlikely to be the case, pressure they actually allow as a possibility for your answer. So even though in my mind it can only really be rainfall as a sensible answer, but actually allow pressure as well, which I think is quite generous. So because of that, we can put pressure or rainfall. I'd definitely be going for rainfall personally. So state the units that are used in the large data set for this variable. So if you did go for pressure, which would be strange but allowed, it'd be hectopascals, or if you put rainfall, which I would suggest you do, rainfall's measured in millimetres, which you can put as either mm or right millimetres. Finally, worked example 5. So this time, Sam is investigating the weather throughout the year in Herne. He uses the larger data set to investigate the daily mean wind direction, and Sam believes that each cardinal wind direction is equally likely in Herne. So let's assume that he's correct. So for part 1 of A, assuming he's right, State the probability that the cardinal wind direction in Herne on a randomly selected day is north-northeast. Well, how many of these cardinal wind directions are there? So I'm just going to remind you of the diagram with them all on, not just north, east, south and west, but of all of these subdivisions, there's actually a total of 16. So north-northeast, this one here, is just one of 16. So if each direction is equally likely to be picked, then north-northeast just has a 1 in 16 chance of being picked. So the first one, 1/16. Now part 2 isn't actually on the syllabus until later on, but I'm just sort of diving ahead of where we need to be, because it's just worth mentioning for a few moments, this one I think, because I've seen this distribution crop up a few times in 1-mark questions. So what distribution is it I'm talking about? Well, this distribution that you could use to model the probability of each cardinal wind direction in Herne on a randomly selected day is called the discrete uniform distribution. It's a special type of distribution where each outcome has exactly the same chance of happening. So for example, flipping a coin, heads and tails, half and half. This one I've shown you here is rolling a dice. There's 6 different values on the faces. If it's a fair die, the chance of each one of these faces occurring is 1/6. So it'd be the same discrete uniform distribution idea for these wind directions, just here, instead of 1, 2, 3 for the dice, it'd be north, north-northeast, northeast and so on, and the probabilities for each one would be 1/16, 1/16, 1/16. So that's what it's called the discrete uniform distribution. Sam now decides to investigate the daily mean wind direction throughout the year. It says state one limitation of using the data for Herne from the larger data set as a sampling frame. What you need to remember is that data is actually only available from May to October in the large data set, so it doesn't represent the overall picture for a full year. So that's one thing you need to remember about what's in and not what isn't in the large data set. It's only 6 months out of a full year. Another thing you could say as well is that they only have 2 years in the large data set, 1987 and 2015. So again, you could say that it's not a very good sampling frame because of the lack of years. So there's 2 different things you could say for B. I'd probably just say that it's only May to October. Finally, for part C, we have to explain how to use simple random sampling to select 36 days from a year. There's a few ways of doing this, but I think the easiest is to just go with the calculator description. So we'd create a sampling frame of days by assigning each day of the year a whole number from 1 to 365 days inclusive, or if it's a leap year you're in or he's in, could be 366 days, including the 29th of February. Then on a calculator, we could use the random integer function and type in 1,365, or indeed 1,366, and that would then allow us to generate unique random numbers between 1 and 365 or 366. Each random number that's generated would then relate to whatever day has been assigned that particular number. And if any number is generated which has came up before, just ignore that repeat and go again. So that's one way you could describe part C. I think the easiest way now for getting random numbers is a scientific calculator. So that's all from me. That's over to you to try some. So in your books, if you turn to page 12, it goes on to page 14. Just try exercise 1E on the large data set in the Stats and Mechanics book. I'd suggest questions 1, then question 3 and 4, and finally question 6, question 7, question 8. And if you get stuck, you know where to find me. Thanks for listening, and I'll see you all soon. So goodbye from me.